Okay, this is a lesson that gives an introduction to complex numbers. I'm going to cover quite a lot of material. There may be times where you want to pause and replay or consider some of the things being said. First of all, a definition. We define an imaginary number as having this characteristic: I squared equals -1. You may think this strange because in your experience nothing that is squared gives a negative result, but this is part of what makes an imaginary number. If I squared is -1, then I itself, the imaginary number, is the root of -1. Again, something that we've never been able to evaluate before, not as a real number, but these are imaginary numbers. It's a bit of an unfortunate name because it gives the image of pixies and fairy dust, but imaginary numbers are very important and they are used in electronics and other real situations. They just can't be called real numbers, but they very much exist. If I take imaginary numbers and real numbers together, I get complex numbers. They typically are written in the form a plus bi, a being the real part, b being the coefficient representing how large the imaginary part is, and I is the imaginary number itself. Now, a bit about operations with these types of numbers. To add them, first of all, consider what I do with radicals. If I had the sum of these two sets of radicals, I would combine the real parts to make 6, and I would add the radical parts to make 10 root 5, because they are like terms. Well, it's just the same with complex numbers. If I had 2 plus 3i and 4 plus 7i, the 2 and the 4 combine as real parts to make 6, while the 3 and 7 combine to make 10, I, imaginary part, because again, they are like each other. Real parts are like, imaginary parts are like. When it comes to multiplication, let's work with the same expressions, 2 plus 3i, 4 plus 7i, and we know that FOIL gets us an expanded result. So I'll use FOIL, first, outer, inner, and last. But remember, right here, that I squared is -1. So this is actually 26i, those are like terms. But the 21i squared is actually the number -21. Okay, so I'm going to make a note about that. Squaring imaginary numbers gives a real result. This is an important property of imaginary numbers. I can combine the 8 and the 21 to make -13 plus 26i. When it comes to division, what we're going to do when we're dividing complex by complex is we are going to write what's called the conjugate. And you have seen this in the past with radicals. Okay, the conjugate is a binomial with the opposite middle sign. And there's an important property. These are called a product of a sum and a difference. And what we get is a difference of squares. That's the pattern that you've learned in the past. So I will write 4 squared, and then I'll write 7i squared. The numerator is a FOIL process, so let's do that. 8 minus 14i plus 12i and minus 21i squared. Okay, again, we remember I squared is -1. This is actually the term positive 21. Combined with 8 makes 29. And these imaginary components are like. I can combine those. The denominator, 4 squared is 16. I squared, well, that's -1. 7 squared is 49. So this is actually, you know what, I've written that wrong. That should be a minus there. I don't know why I put a plus there. This should be I squared, which is -1, and 7 squared is 49. So this is -49 being subtracted. Therefore, it's positive 49. And so finally, this leads to 29 minus 2i over 65. And observe that the denominator is real. Denominator is real. So multiplication by the conjugate produces a real denominator, and that's a simplified way of writing division statements. Complex conjugates, a note about that. We often write a plus bi, a complex number, with the term z. A minus bi is the conjugate. It's often denoted with z and that asterisk on it. So z asterisk is the conjugate of z. These occur in quadratic equations where the discriminant is less than 0. In the past, when the discriminant was less than 0, recall that that was in a square root, so we said no real solutions. Well, with complex numbers, we get solutions, but the solutions now are complex answers. Let's look at an example of what this looks like. So we're going to revisit quadratic equations. Here's a quadratic equation. We're going to solve it with the quadratic formula because it's not factorable. So I would write x equals positive 4 plus or minus negative 4 squared minus 4, a is 1, c is 5. All of that is in a radical, and it's all divided by 2 times a, which is 1. Alright, observe that I have 16 minus 20. Well, that's negative 4. We would have stopped in the past and said we can't do anything with this, but not anymore. Here's what we're going to do. We're going to write this as root 4 root negative 1, knowing that the radical of a product is the product of radicals. Okay, that root 4 is going to simplify to 2, so let's factor a 2 out. 2 plus or minus, actually, I'll hold off a step, I don't want to confuse you. 4 plus or minus 2, now remember, the root of negative 1, that's I. There's the imaginary part coming in. Now, observe the 4, the 2, and the 2 have a common factor of 2. So let's factor out the 2, and we'll divide by that common factor, leaving the roots x equals 2 plus or minus I, complex roots. Previously, we would have said no real roots. Well, they're complex. This leads to a theorem for complex roots of quadratic equations. We say that if c plus di and c minus di are roots of a quadratic equation, like the example I just did above, then the quadratic equation has a very special structure. And the structure is x squared minus 2 times cx plus c squared and d squared equals 0. Whenever x squared has a unity, meaning 1, coefficient. If you look here, coefficient of 1, this will be true for this. So let's put this to work and look at an example where we're going to find all quadratic equations with real coefficients and the roots 2 plus or minus 5i. Okay, well, we know that when we're working with quadratics, we try to think about numbers that have a certain sum and a certain product. So the sum of my roots are 2 plus 5i plus 2 minus 5i. Well, that forms the real number 4. The product, 2 plus 5i times 2 minus 5i, is going to form the answer 4 minus 25 I squared. I squared is negative 1, so this is like 4 plus 25, or 29 is my product. Okay, using this knowledge, the form of the quadratic is going to be based on these numbers I just found. The form of the quadratic is x squared, there's the sum being used, there's the product being used. Now this is a specific case of a quadratic with this sum and product. The question asks for all quadratic equations Well, I can always have a scalar multiple. Any number a multiplied by that quadratic will still have the properties of sum and product. So this describes every quadratic equation with the roots 2 plus or minus 5i. And I should just make note, this is for real coefficients, a being real, 4 and 29 being real numbers. We won't deal with complex coefficients.